for a little bit of context then, obviously, yes, I was a Fung Scholar quite a while ago now, about 5 years ago. And since then, I've done a lot of things, but I was a biochemist, and the area I've slipped into has been a lot around materials technology and novel materials development. And I think it's quite interesting, some of the things we've talked about today, more in the area of sort of finance and cross-border payments and trade, which are in some sense esoteric, but a lot of the problems that were just being discussed there by Barbara and Pamela and the others were actually quite similar. Things about standards, things about clarity, and about mutual understanding of what's meant to be achieved. And actually, you know, the replacement of plastic is a very popular trend. It's something I think very few people would express objection to. But actually today I'd like to run through a little bit some of what's been going on over the last 10 years or so, some of the problems that are currently still there, and what this really boils down to when you as a consumer or as a business owner or decision maker are choosing materials and thinking about the effects that that can have. So to start with, we'll quickly go over obviously why we are trying to do this. And then we'll look very briefly at the alternative materials landscape. We'll talk a little bit about how assessments of materials and plastic alternatives are generally made and some of the issues that arise through the use of what are called LCAs or life cycle assessments. And very quickly, we'll sort of wrap up and turn this from what will be quite a whistle-stop tour of material science and environmental impact into something a little bit more pragmatic. So to start with then, the issues with plastic are pretty well known and I think aren't going to be very surprising to anyone on the call. We do dump a quite incredible amount of plastic currently into our environment. Roughly every day, we will dump 8 million pieces of plastic into the oceans, and over a year, that totals about 12 million tons. Now, the problem with plastic is obviously not just its presence, its volume, it's also how long it persists in the environment, because if we stop today dumping or producing all plastics, the plastic we've already dumped would take longer to naturally degrade in the environment than the entirety of human history to date. So we are creating for ourselves still a challenge, but we have a challenge in undoing what's happened already. And the reason that increasing pressure is coming onto companies and materials producers as well as users is that the health impacts of this are increasingly clear. So microplastics are one that we're all pretty well aware of, and they're increasingly linked to various inflammatory and autoimmune conditions. And additionally, there are sort of petrochemical polymeric materials like PFAS, which are included in a range of products for a range of reasons, and are what are also called sort of forever materials. They're very slow to degrade and have been linked to things like cancers and a range of other negative health outcomes. Now, the problem here, though, is to think about those numbers in a little bit more detail. So 8 million pieces of plastic a day. Where is all this coming from? So I think we will bring a little bit of Q&A into this session now, and I'm going to show you some images, and I'm going to ask you to take just a few seconds to think, and then have a guess roughly how many pieces of plastic are in that image that you're seeing. So firstly here we have fabric conditioner aisle in a supermarket. What are we seeing? There are some bottles, there are boxes, little plastic labels, runners, maybe the shelves themselves are plastic, but let's assume they're metal. Ooh. So would someone from the audience like to have a quick guess at roughly, to an order of magnitude, how many pieces of plastic are we looking at here? You can probably already sense that there's a slight trick to this question, but would anyone like to suggest? I can see some people doing what looks like counting, and I'm afraid you might all be a little disappointed. 10 to the 3. That's not a bad shout, or 10 to the 4. So I think we might still have an issue with muting, but 10 to 3 or 10 to the 4 is not a bad argument at all. You know, there's probably about 1,000 units here of product. They've probably got 3 to 4 components each. And then there's various other pieces of plastic. Some are going to be more complex, less complex. But actually, we are looking here at something more like 10 to 100 million pieces of plastic, maybe more. And the major reason is not any of the plastic that you can see in the image. It's not the linoleum floor tiles, it's not the bottles, it's not the wrappers, it's not any of those physical objects. It's the fact that almost every fabric conditioner on the market today contains what is called microencapsulated fragrance. So fragrance oils are extremely volatile, they evaporate very quickly, and that means they lose their smell effectively for us quite quickly. So to avoid the cost of adding lots more fragrance oil, what most fabric conditioners use is fabric oil which is contained in a microscopic bead of plastic. And any one of these bottles will have about 1 million of these plastic particles in. They deposit on your clothes, they wash down the drain. Their only purpose is to reduce the cost of fragrance oil, but they are released in massive quantities over the course of a year into our oceans and watercourses. And unlike big objects that we're familiar with, like bottles, there's no way to collect them or to prevent their release into the environment. So for the next image, we have something like this. So again, we'll play the same game. There are some really obvious pieces of plastic here. There are things like the lids on the cups. There are the little packets of sauce. There's things like the tray. If you counted all that up, you might say there's a few dozen pieces of plastic here. But again, we're looking at a very similar situation, but for a different reason. And that's that any of those apparently paper pieces of packaging that are being used here have been coated in plastic. And they've been coated in plastic to prevent grease staining, to enhance printability, and in the cases of things like the cups, to enable them to hold water. And again, this is a huge area of plastic use, this kind of plastic coating application, which is very, very hard to perceive, very hard to notice when it's in use, but is particularly harmful because it's not possible to recycle plastics in this form. They either enter the watercourse during paper recycling, or they cause what's called clodding in paper recycling streams, which is burnt ultimately. And as a wet burn, as you can imagine, it's smoky, it's not particularly efficient, and it releases quite a lot of particulate matter. So while generally we tend to think about plastics in terms of big rigid objects, actually a lot of the excitement and a lot of the drive in the alternative materials space has been about tackling these kinds of single-use, non-containable plastics and polymers. And to do this, we won't dive into it today. I've spent about half a decade in this space, and I certainly don't know all of it. There is a huge world out there of alternative materials. And if we ignore natural materials and stick with the sort of biomaterials you see today, they can come from things like animal materials like milks or collagen materials, things like casein. They can come from bulk plant matter, so things like lignins, celluloses, or they can come from semi-processed agricultural products. And those are things like sugars, oils, protein extracts. They can be processed, and here there is a big division between things that look like petrochemistry, they're industrial chemical processes, and things which are biochemical processes that take place in fermenters or bioreactors and rely on living organisms to convert the chemicals of those objects. And what we end up with are a huge range of materials that are appropriate for a whole range of different things. And this is where we start to get into the complexity, because every time you look at a different application, you're running against plastic and you're comparing your material in slightly different ways. And this is a very complex landscape, but there are some quite common problems that have come up over the past 15 or 20 years of development. And those are around the impacts of agriculture. So if we're using biological materials, we have created an environmental impact in farming and harvesting that crop or raising that animal. There's the processing. So some of the processes you may be surprised to find for biomaterials are actually very, very polluting. Reconstituted celluloses are the classic example. There is now a very, very clean way of making cellulose fibers, but most cellulose fiber is produced through a very, very toxic and harmful process, which is banned in a great many countries. Then there's efficiency, and this applies to broadly any new material. Plastics have been made for a long time. They're made very well. They're made very efficiently. even quite a controllable chemical process requires some time to get the efficiency dialed in. But whenever you talk about something that's involving a fermentation or a bioreactor step, you're going to be losing a huge amount of feedstock to side reactions, to undesirable products, and to the general metabolism of those cells. And then the other elephant in the room is around the actual end of life. So we set out to do this because plastic is bad. Plastic pollution is a bad thing. It's harming our environment. And that often leads to a false assumption that any biomaterial that we can find and source is improving the end of life compared to plastic. And a case study of where that's not really true is something like polylactic acid. So on the right, there's a common sort of advert or advertorial for polylactic acid. And this is a great example. It uses a lot of sugar, which has very high environmental impact. It wastes most of that sugar in conversion. And finally, it claims to be biodegradable, but it is only really biodegradable in a special kind of industrial composting setup where the vast majority of it will never reach. If it's in the soil, if it's in a home composting environment, if it reaches the oceans, it will not effectively biodegrade. Now, to deal with these problems, when we're trying to compare all these things, LCAs or life cycle assessments have become a really popular tool. And they try to make the ESG space simple by turning some very difficult questions about material use, process selection into very clear quantitative metrics. And on the right, you can see an example from energy generation where it's comparing the CO2 emissions during generation and during setup for a variety of different sources. But the problem with LCAs is that under the surface, they're always making difficult choices, and it's often not clear exactly how they're making them. And the major one is weighting. And these have all sorts of metrics. There are various accepted methodologies, but basically you're trying to balance up how much you care about one impact versus another. And very commonly, because CO2 and global warming are a major discussion point at the moment, even for things like plastics, you're often talking about how much do you care about greenhouse gas emissions versus everything else. And there are ways to set these up and different approaches that are taken, but they are essentially hiding quite difficult choices. So CO2 and greenhouse gas emissions are about global warming acceleration. Things like water pollution have quite real impacts on local ecosystems. And the problem is that these methodologies are not always clearly articulated and aren't always clearly understood by companies using these LCAs. And it's a very tough one when we take the perspective of plastics, because in a certain sense, plastics are not a bad material. If you really care about CO2, most of the time plastics will beat out, in most applications, biomaterial alternatives. And therefore you are having to make a tough choice in all of this about what problem you're really trying to solve by swapping out materials. And that's one where there's been a lot of progress over the last sort of half a decade or so, but companies still aren't all the way there on understanding exactly what they're choosing when they're choosing an alternative to plastic. And I should say, you know, I'm got some skin in this game. I work for a plastic replacement materials company. We specifically don't target things like big rigid objects. We target things like microparticles that will be released. But all the same, we have to be very explicit about the fact that we probably have a larger CO2 impact than most of our competitors and most petrochemicals. And this is partly, I think, similar to what Barbara was saying, that there was some uncertainty in that statement there. And that's because for smaller players, newer materials, it's very hard to quantify effectively in an LCA format exactly the impacts that you're going to have at scale. So this has really been a quick tour, and it's been largely negative. And I think my general tone often tends to be, but there are some useful ways we can all take this information and apply it when we're thinking about plastics and avoiding them in our day-to-day life. So one thing to think about is, what is the end of life of this object that I'm holding? If it's something like a rigid bottle, those are actually quite well recycled, and there is a stream for plastics that is quite efficient. If it's something like microencapsulated plastics or plastic coatings on materials, those are areas to really try and avoid non-biodegradable polymers. The application is also important because often we've discussed biomaterials may have a large footprint compared to plastics, but often the impact of the material as a whole in application is quite small. So high value items, things like refined enzymes, pharmaceutical products, medical devices, electronics, the impact of the cargo itself completely outweighs the packaging. You could package them in almost whatever you want. What matters most is maintaining the unit inside and not having losses during transportation, etc. And then finally, the other point is that we all need to think, whether this is at work or in our personal lives, about what we think about weightings. If we're troubled by plastic, if we're upset about plastic pollution, we have to understand that solving that is not necessarily aligned to solving things like greenhouse gas emissions and other kinds of environmental impact like water pollution. And just keeping that in mind can be very helpful because, as I said, there are certain kinds of plastic that we deal with on a daily basis, which are wildly bad in terms of their microplastic pollution impact, and replacing them may have quite a minimal impact on things like greenhouse gas emission. So that has been a very quick tour through a very complicated space. I'd like to thank you all for taking the time to listen patiently. I think I have just about run to time, so I will kick this open in case anyone has any questions, anything they'd like to raise about this, or anything around biomaterials generally.
Well, thank you very much, Stanley, for your project and for sharing with us the concepts like LCA and weighting. I think our audience would be quite surprised to know how ubiquitous plastic products exist in our environment. So let's see if there's any question in the chat room about what you have just shared. And if not, I will have one question for you actually. Now, you mentioned about the alternative materials. So I think the major obstacle we're facing is the issue of cost. So how can companies actually bring down the cost in manufacturing such alternative materials so to replace plastic, given that the plastic products are so ubiquitous in our everyday life?
I think that's a very good question. I think it's been a big shift over the last decade away from a previous attitude, which was that, of course, people pay a premium of 2 times, 3 times, sometimes 5 times the traditional plastic to replace it. And I think you're right in saying that that attitude is basically dead. Right. Particularly at the moment, nobody is paying a green premium for anything. But I think that chimes nicely with particularly the focus of the company I work at, Zampler, and in my role there as head of commercial strategy. The focus there is really on some of these more specialty plastics. And so something like polypropylene PET is incredibly cheap and incredibly hard to compete against in bulk application. But actually a lot of specialty polymers are quite expensive. So something like polyvinyl alcohol, which isn't that special. If anyone's ever used a Tide Pod or a soluble pouch on a dishwasher tablet, that's polyvinyl alcohol. And that costs about £25,000, about $29,000 odd a ton. That is almost 10 times the price of other traditional bulk plastics. And if you go further into specialty areas, some of them are very, very expensive. So I think what we're seeing now is a whole new generation of biomaterials that target individual specialty polymers. They know they're very expensive. They know the specific things they have to do in a certain subset of applications. And aiming at that price point is much more achievable, even at quite small scale manufacture.
Right. Thank you for your answer. I hope that the alternative materials would be more common in the future. Right. So thank you, Stanley, again.